So this is our final video lecture on prior distributions, an important and controversial topic in Bayesian analysis. And in today's video lecture, we will look at non-informative prior distributions. We will look at two topics. The first is the non-informative priors. We'll examine what that means, and then we'll summarize the approaches to prior distributions for Bayesian analysis. So what is a prior with no information? Well, if we don't really know in advance much about the parameter that we may be estimating, it's still appropriate to use Bayesian analysis and to do it with a prior distribution that reflects this lack of information. Suppose, for example, we're uncertain whether an event will occur. The prior should give us a probability of 0.5. Because it's effectively an equal flip of a coin. It could go either way. Conveniently, a uniform prior distribution over 0, 1 does this, since the mean of the uniform at that range is 0.5. This is also known as Laplace's principle of insufficient reason. Laplace is considered one of the founders of modern probability and statistics. And his principle basically says, without further knowledge, you should assume a uniform distribution. There are three problems with Laplace's principle that people have argued about over the last couple hundred years. The first one is that it leads to improper prior and improper distributions. The second one is that it's not coherent. And the third is that it's not invariant under transformations. So let's take a look at each of these three and show why we can still use Laplace's principle, and it works quite effectively for us. Let's look at the first argument against using this notion of a uniform distribution as a prior. And the argument here is that it leads to improper priors. To see this, suppose we have a parameter, say theta, and it's over the entire real line. What non-informative prior will work? Well, if we try a uniform, for example, if we set our prior distribution equal to some constant, and then we integrate that over the entire real line, we get something that is improper in that it doesn't integrate to a finite solution. In particular, it doesn't integrate to 1, which is the requirement by the axioms of probability. So in this sense, it's an improper distribution. But an improper distribution, in this case, prior doesn't really matter to us because of the way that Bayes' rule works. And we can see this again with a simple example. Suppose we have a random variable x that's sampled at n time or at n points, and it's from a uniform distribution. And the uniform has a mean of mu and a variance of sigma squared. And we know what the variance is, so we're just going to concentrate on estimating the mu parameter. Well, if we assume this improper prior, we set f of mu equal to 1, then clearly this is improper because it will, in fact, integrate to something that's not 1. It'll integrate to something that's infinite. It's unbounded. But nonetheless, if we use that prior in Bayes' rule, then we see that the posterior distribution on the left-hand side is just going to be proportional to the likelihood function times, in this case, 1, which is the prior, which just returns the likelihood. And so, in fact, what we're getting is the standard frequentist approach to probability and statistical reasoning, which is known as the maximum likelihood approach. So all we're doing is we're returning the likelihood function in this case, and the solution, the estimate, is the maximum likelihood solution. So in this sense, frequentist statistics are a subset of Bayesian statistics. They occur when we, in fact, know nothing about the prior information, and we have an improper prior that we're using to represent that. It is, however, possible to not, if you're concerned about the propriety of the prior distribution, it's possible to get the exact same solution, a maximum likelihood solution, by letting, in this case, the variance of the prior go to infinity or get extremely large. As we've seen in previous examples, as the variance of a Gaussian gets very large, it gets very flat. It's still proper, but it's just becoming extraordinarily flat on the real line. Okay, let's take a look at the second argument against using a uniform or using Laplace's principle of insufficient reasoning. Solutions with a uniform and non-informative prior do not make sense is the incoherent argument. And the famous example of this is the question, does life in the universe exist outside of the Earth? Well, if we use a uniform prior, then we're going to answer this and say, well, it's 50-50. In fact, we don't really believe that anymore. We think the likelihood of life existing outside the Earth is much better than 0.5. And why do we do that? Well, it's because if you start with a uniform prior, you have to get it over the correct sample space. So this is an issue of correctly defining the sample space. So instead of looking at the sample space as a binary, 0, 1, life either exists outside the Earth or it doesn't, a better representation of that sample space is of planetary events. And there are many billions of planetary events out there, any one of which could produce life. And as a result, we think that the probability is much higher. So this incoherent argument is really an issue of getting the sample space correct for the uniform distribution. So we can make the argument that when non-informative priors are well defined over a sample space, they are in fact coherent. Okay, the final issue is not being invariant under transformations. And this is really a very much of a technical issue. It has only modest practical importance in most real problems. But if you're interested, there are solutions. One of them is what's known as the Jeffreys prior, and the other solution is what's known as the reference prior. And these solutions can be used to deal with this notion of invariance under transformation. So essentially, the non-informative approach then is a fine approach to use when we feel we have no information to bring to the problem that we're working on. All right, so let's summarize then the approaches to developing prior distributions from the information that we have for Bayesian analysis. And the first point we made is that a prior information is not the same thing as a prior distribution. Typically, we have more information that's available to us than we can put into a distribution, but this is better than not putting any information into it, and in general, that's why Bayesian analysis is so effective, is because it does bring to bear that additional information that we have about the problem. The approaches to building a prior distribution for Bayesian analysis, the first one and the most commonly and used and highly recommended is to use base rates. If you have base rate information, for example, you know the rate of infection within an area, use it. Use that base rate information, but you may have to modify it based upon what you know about the particular population that you're going to apply it to. Subjective approaches, the argument here is use only when you have really good experts who really know what they're talking about. And even then, be very cautious. Subjective approaches typically can lead to problems if you don't correct for issues that humans frankly have, even very good expert humans have when it comes to trying to estimate probabilities. The maximum entry approach is, again, a very technical approach. Look it up and use it when you are working on a problem that you absolutely have to justify your choice of prior. The conjugates that we've spent some time on, this is a good general purpose approach that can deliver very fast results and that you can get a closed form solution to. And finally, we've looked at non-informative priors. This is often a good starting point. If you're starting a problem, you really don't know very much about the domain, a non-informative prior is a good place to start, and it works very well. In fact, as we've seen, it is in fact the maximum likelihood solution, the frequentest solution to problems, which, as we pointed out then, makes it a subset of the entire Bayesian approach to problem solving. Okay, and that concludes our discussions of prior distributions and prior information.